Hello students, so let's try to go to the next video for the group theory. In the last 4 video, we have just tried to discuss what is definition of group and two or three different examples related to discrete groups. So here today we will just go for a very interesting concept all about the multiplication table. And this multiplication table also known as Cayley's table and which is mainly named after the British mathematician Cayley, Arthur Cayley actually. So what is this particular Cayley's table? And this is mainly for the finite group. Okay, so this is for the finite group. So this is a very nice way and very efficient way to check whether the collection of elements or collection of operations belongs to some group or not. So it has some rules, some norms, and we have to, once you are going to follow that particular thing, then you can easily just check whether the following collections are going to follow the rules of group or not. So what are the multiplication table? So suppose we have a some group and which is n dimensional or nth order group, and suppose we are just going to represent as a naught, and a naught is just our identity, and what I have a1, a2, ap, am, and finally hence it is nth cross n order group. So we have n minus 1th element is there because a naught is denoted by e. So we have this much of basically these are the elements in the group. So what we have to do, we have to just create a n cross n. We have to create n cross n table, and that n cross n table follows some basic properties. So how you will create the table? So first you will just start from the identity. So here we have identity is identified as 0. Then we have A1, then we have A2, and we are going to arrange in a row. So similarly, we will go AP, and similarly, we will go AM, and finally, we will go AN minus 1. And similarly, we will just go for writing the column also in the same manner. The order must be same. So what will happen? Suppose we will go A1, A0, and then we will A1, then we will A2, and finally we will go for AP, and then we will go for AM, and finally we will have AN. So these are the basically arrangement of your elements as in a basically Cayley table, and here you can give the operation. You can define what is the operation. And suppose I am talking about this particular, and every element is just about the operation. So what will be this element? This element is operation between A0 and A0. This element will operation between A0 and A1. So what will happen? The first row and the first column will be just tell you operation with the identity. So what will happen? A0 will go to A0. We will have A0. A1, A2, and we will go AP, we will go AM, and we will go AM. And similarly, this will be exactly same. We will go for A1, A2, up to AP, up to AM, up to AM. So first row and first column will be just operation with the identity. And if you are just trying to see the matrix for any particular element, the matrix element, suppose we are talking about the matrix element of this particular group, M and P element, MP element, M cross P element. So what you have to do? MP element will just tell you about the operation for this particular element, will tell you operation between AP, operation AM. So similarly, if we are talking about this one, this will just tell you A2, operation A2. So this is the way we can represent it, but one should always take care of some more information and some more property. So what is the first property? In the first property, what you have basically that every element will come once in a row as well as column. That means if A2 will come here, then A2 will never come into this particular row and A2 will never come into this particular column. Suppose AP will here, then AP will never come into this particular row other than this one, and neither it is coming into this particular column. We will just try to do one example and we will just find how we are going for this one. And in each and every row, there must be inverse as well as identity element. Yes, that is the same thing what I am saying into the first property, but I am just going to elaborate it separately. In each and every group, in each and every row and column, in each and every row and column, there must be identity as well as inverse group. Sorry, inverse element, not group, inverse element. Inverse element. So you have to just follow all these rules and you can easily write all the elements with the operation in this particular matrix, and whether you can check they are abelian or not abelian. If you will find A operation B is equal to same B operation A, then obviously it is abelian, and you can easily use this particular Cayley table, which will just increase your efficiency to analyze the problem of a group. So let us try to use this particular multiplication table or the Cayley table in one particular problem. So let's try to go for this one. So we have a finite group, and let's say this group is defined as E A square, and it is also given that A cube is equal to 1. And what we have to do, we have to just make a Cayley table or multiplication table for that. And E is identified as identity element. So obviously this is a 3, the order of this group is 3. So the order is 3. So what will happen? We have to just make 3 cross 3 a matrix. So how you will go for this one? So just we will go for E, that is identity. Another is A, another is A square. In the same manner, in the same ways, first we have to go for the column. So it is A, E, A and A square. And what is the operation? The operation is simple multiplication. And it is also given that A cube is equal to 1. And this is something like your cube root of unity and something like this type of property. So just go for the first one. So we have to just go for 3 cross 3 matrix. So what will be the first element? This will be A square. So E operation E is just E. E operation A is A. E operation A square is A square, because E is just an identity element. Identity element. Now let's go for this particular column. Sorry, this particular row. So A into E, A operation E is equal to A. A operation A is basically A square. And now A operation A square is nothing but E, because A operation A square is A cube and that value is E. Now A square E is A square. A square A square operation A is A cube is identity, and A square is A4, and A4 is nothing but A, because you can write A4 as something A cube into A, and A cube is 1, so that value is 1, is A. So now we have to check whether this multiplication table is correct or not. So how we will go for this? So what we have, you have to just check. In each and every column, we have separate, you have a different element. Look at here. This A square is separate. A square, E is separate. A square, E and A is separate. So you have a different thing. And now you can also check that what is going to happen into the every row. So every row you have, sorry, this is your basically row. So every row you have different element. Just check. In every column you have different element. You can easily check here. Every column you have different element. And you have identity element in each and every row as well as every column. So you have identity here. Here is identity. Here is identity. And you can also check inverse element is also there. So you have A square is inverse of A, and similarly A is also inverse of A square. So thus here is the inverse element is also there. So you can easily make this type of table and you can calculate and you can just check whether they are forming a group or not in a very efficient manner. So this is a very simple problem. That's 3 cross 3 matrix. And obviously you have to leave this one. You have to only talk about this particular elements. So this is element 1, 1, this is 1, 2, this is 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. So you can easily check and you can easily find what is the inverse, what is the identity, and what is and how your operation is going to work. So students, you can just practice to this particular Cayley table, and this is very important to do your group theory, to apply your knowledge of group in a very efficient manner. Thank you.